Well, hello everybody, and welcome. Welcome to this very warm, steamy room. Hopefully, it'll cool down as we occupy it. And welcome also to the folks that are joining us online. So, really pleased today to welcome Ed Verhamme, who is a senior and principal engineer over at Limnotech, just down the road. Ed did his undergraduate degree and his master's degree at Michigan Tech, where he studied engineering. And he's now works for Limnotech and also has started this new startup company called Freeboard Technology. And Ed is really engaged, I would say, in science with the public and with professional societies. He's really active on social media. He served as the president for the International Association for Great Lakes Research, and he works really closely with many folks in this room. At Sigler and Glurl. And today he's going to tell us about applying new technology at a Great Lakes scale. What are you waiting for? Thanks, Ed.
Thanks, Greg. I was hoping the U would be an animation. I forgot to make it animate, but the talk was, what are we waiting for? And as part of this, I want to get to what are you waiting for? And I want to talk through a little bit of why this matters, how other industries have sensorified everything. What are some barriers to the environmental field? Like, what's different about how we apply technology that has worked, that we've seen some really good success applying technology at a Great Lakes scale, and just trying to help keep up with the technology. So I'll be hanging around afterward. There's going to be time for questions. I promise I'll watch the clock. But let's jump in. Here, hold up. I've been showing this slide for a couple years now, and as an engineer, trained in all the things engineers do, there's a lot of options that we have, all the way from monitoring the environment to presenting that data to an end user. And in my exposure to the science community, they generally have one version of how they're trained and how they apply and use this. When you think about the industry as a whole, the hundreds, thousands of companies that are making sensors, the data loggers, and as technology advances, we don't ever really lose those original options. So if you were trained on a YSI, you can use the YSI your entire career. But what you might not be exposed is different prices, different implementations of that tech, how to have that tech made for the way you think it should be applied. So I think I spend a lot of time thinking through different options, scales, prices. What do people know? How do we help transfer that into a physical object or a sensor? And Greg brought up the difference between Limnotech and Freeboard, and I think the new technology company actually helps us build and then use that technology at a very small scale. So even if we build a batch of sensors that weave through this, we can apply and use those on a project. Brief overview, just talking about the value of sensors. It's not always apparent why is there 1,400 microchips in one car? Like, they must provide value. That's an incredible cost. Lots of things that go through. That value is there. We keep adding more. So how do we talk about that more openly? How do we help connect who's using the sensors or who's benefiting with who's paying for them? We know when you sell a car, you're paying for that. Someone else was a part of designing it. So when we get into public-private work, we tend to kind of remove who values it to who pays for it, the timing of that. How do we help at least know how to connect that value? Talk about a few case studies, and talk about small-scale manufacturing. And I think this is where I've tried to apply engineering at a small scale that has really helped advance some projects, and wanted to just show you some of the components and tools that we're using. jumping into cars, I didn't, my title was a little bit more provocative. I was hoping to go a little bit more in depth into why is there so many sensors in cars? Like it's hard to get inside those engineering teams and those proprietary products and timelines. But what I did found fascinating in my research is the incredible amount of expense that's associated with the car's electronics these days. And if you think about all the features you're using in cars, how do manufacturers get an edge? It's usually electronics based. It's not that the metal cylinder is 10 times better than the other one. It's some feature set, it's some safety, fuel economy, space efficiency. So by 2030, they estimate that 45% of a car is going to be in the electronics, just all the different instrumentation and features. It's not saying that those other things in the car aren't expensive either, but the manufacturing has really optimized the amount of steel, the amount of aluminum, the price it takes to do that. So I've seen a similar trend happen in other industries too, is that value of the electronics and the importance of it becomes important. And smart cars, and what we're getting to is every little semiconductor and electronic sensor unit serves a function. There's tons of raw data being streamed internally to the car. Only very small amount is actually needed or condensed to make a decision. Should I trigger that airbag? Terabytes of data you could save forever that would basically say, no, not right now. So I try and think about our scientific applications of those. How much raw data do we need? How do we think about the decisions that need to be made, and not be shy about using high frequency sensors? We might not need to save all that. Or where do we save it for research and then think about the applications? So these decisions, cost trade-offs are a very common engineering practice. They apply it to every little subsystem of a car. And we are in Metro Detroit. I think if we wanted to explore this concept, this thought, the cost, the revisions, it'd be good to think about that for applications to science. Smart houses. Cars seem a lot more organized to me. Like the car, you have to buy it and it's got to move and it's got to last. Some of the smart house stuff, it's a mess. Like if I think about my home and what's smart, when I bought it, how it works, it's really messy. I don't know where the smart home goes. I've seen sort of the smart home of the future that's all integrated and everything works well, but I don't see that scaling in a single manufacturer being able to have your house be outfitted. So this is maybe a little bit more akin to our scientific community, where lots of different generations, lots of different things are being used within this same house. If we use our Limnotech office as an example, it's a whole cascade of when things change and why. We're generally responding to individual pressures. We can upgrade that now or later, think about how we use it. So again, this sector has lots of engineering, lots of different opportunities to buy the thing, pay a subscription, connect it with Bluetooth, no subscription. Where do government regulations get involved in why these things need to exist? Even smoke detectors in your house, like it's up to you to replace the batteries and put it in. What a part of building a house are those a part of the house? So I'm surprised at how much the individual homeowner is responsible for this. I think the electric utilities play a role here. DTE just sent me a message the other day saying, hey, your gas meter's 60 years old, maybe we should replace it. And they scheduled it from this modern fancy smart meter that I have an app now that I can see. It's up to them. I didn't really have a role in that. So again, you all know the boundaries of your property, your house, what goes in it and why. It's kind of left up to the individual user. At some level, people in a neighborhood could think about, hey, what sensors do we want in our neighborhood? How do we work together around community solar? So I think there's good examples of how you take what you own and know versus how you work together, share Wi-Fi, things like that. So again, I just wanted to offer a perspective on another industry that is tackling some same problem. Like, what decisions do people need to make? What tech should be used there? How is that made? How do we encourage competition? How do we help just be an open demonstration house for this tech? Dollars, you know, the other challenge I see for the environmental sector is how to actually intersect that value with the sensors. So like, how do, in your smart home, this is the US smart home market is projected to be in the many billions of dollars here. We're already at the 20 billion now, only supposed to grow. Most of that you can see is in security and access controls, which my personal experience at cameras, monitoring, all that. So I think it's been interesting to see what's going to grow and why. I think the environmental sensor world has some similar forecast and outlook, and how do we help take advantage of that growth? Switching over to the sensor side, I'll start connecting back to the environmental world. The Internet of Things, the IoT, this has been talked about for about 20 years now. Oops, I don't know what I did there. Oh, we lost the presentation screen here. I can see one monitor, but not the other. It's still sharing online. Is it?
You mind if I
Sometimes tech works and sometimes it doesn't.
Oh. There we go.
See if it gets back to the monitor.
There you go.
Okay, we're back. Okay, sorry technology. Just connecting this back to the Great Lakes. So I think I talked about some sensor density issue. Where have we seen sensors densify? If you look at the Great Lakes, I love this map. Nearest I could find it was from the Canadian Geographic, which I've seen this before, and it's, I believe, related to the Great Lakes Environmental Indicators mapping project, but it shows a really nice, like, where should we have more sensors? Where do people live? Where's industry? Where's agriculture? These are the intersections with water and the Great Lakes, and there's bound to be stresses. So I've liked this graphic. I like to think about how we focus on the dark red areas. The purple is where urban is, and agriculture too. So if we look at the monitoring instrumentation that's floating in the Great Lakes right now, it's you can tell from the Siegel website, about 65 stations. So you look, one car's got 1,400 microchips, it costs so much money. I'm not saying that there's not an incredible expense and work that goes into these, but why isn't there 6,000? Like, where is it a price thing? Is it connecting that last stressor side to the people that are impacted or using it? To me, there's a disconnect, and I think there's been some more focus on open lake science for some of these stations to start, and I'll step into a little bit of the buoy side, but I just like thinking about how can we increase this to 6,500. So part of my talk is simple question: is that needed? Is that necessary? Is there value there? Is there something that we can do to connect the people to that value? I also wanted to show another way to look at the Great Lakes is all the ships moving around. This is a screenshot from marine traffic, and it shows all the ships that are reporting via AIS, which is their ship transponder. All the green ones are big, large commercial ships. There's a teeny tiny case study of those ships volunteering and sharing weather information, but there's probably 10 to 15 maybe online right now out of the potential 200 or 300 ships that are at least using some technology to report their position. So what else could they be doing? They're incredible centers of value. I'm sure these ships are loaded with technology like crazy, and how do we help them be a part of our autonomous or man-powered monitoring of the Great Lakes? And how do we do that at a scale that we've seen technology applied for some other problems? So how can more ships and boats send weather data in real time? One application at a large scale that I think is, I've just witnessed it grow and grow, is the use of technology for the acoustic telemetry observing system, or GLaDOS, in the Great Lakes. This is tracking where fish go. So it's big brother for fish. Each fish they implant with a transmitter, and these are the locations of the fixed receivers that would pick up that. It's kind of like your Apple AirTag. This was a fish nearby, and let me save that. So there's 3,000 receivers deployed today, and you know, there's one manufacturer that makes this equipment, and the fisheries community said, we don't know how we do fisheries management today without this data. It's an incredibly valuable. So I think this is a really good application of, they knew what the application was at scale. The cost might have seemed enormous if you'd have read it all on paper at once, but they connected it to the value of the fisheries management and eventually to the people that fish. My dad knows about this technology. They talk about it in meetings. So I think there's ways that we can use tech, get it down to a scale that matters, and actually scale that up. I'd like to see, you know, how do we deploy 3,000 more? I think the fisheries group would certainly use help, like if we wanted to monitor other things and also track fish movings. But how do we help use these as now assets of opportunity? There's a whole fleets of people that maintain these every year. They have to download the data. So these are not real time. Can we make these real time? Is there technology and a challenge to do that? I said it was just one vendor that supports this. Is there other calls for tech development and applications that would help broaden the technology landscape for fish telemetry and other things that we can monitor as well? I was going to talk about the Toledo Water Crisis in some example. I don't have all the time in the world, so you should just go watch the Erie situation. There's a really good, it's a documentary film that talks about how harmful algae end up in Lake Erie causing problems. The film does a good job of showing the tech that's involved. I think that's another good example of how science was applied and transitioned to a scale that is applied across Lake Erie. I will show just one. Oh, and you can rent it for $3 today, so you can stream it. Put it on your to watch list. I will just connect one part of that that's most interesting for me. This is a plot of the microcystin. Oh, I spelled microcystin toxin wrong. Sorry, the microcystin toxin on the axis, and on the y-axis, and on the x-axis is time. Microcystin grab samples are the triangles, the green triangles. The red tiny dots are the RFU values from the YSI instrument, which is reported every 10 minutes. So the way that the Toledo water plant worked is they would collect a water sample at 8 a.m. At 2 or 3 p.m., they would get that result back for microcystin, which is a lab method. Meanwhile, the online instrumentation, which is the YSI SON, is reporting its relative trend of phycocyanin every 10 minutes. So the plant can react a lot faster to changes and understand time changes between that microcystin sample, especially the time lag involved. So we've been using this real-time instrumentation at water plants across Ohio, and they know that SON doesn't measure toxin, but they know that the SON responds in a way that their grab sample measurement is probably going to respond later in the day. Toledo also isn't required to collect daily samples anymore. They only have to do it up to every 2 weeks or once a week. So they don't run the method if they don't have to, but they certainly want to know what's the relative measure of tox or biomass as measured by phycocyanin. So again, we're able to connect the value of that measurement to their operations and risk, and really use this as a risk reduction tool. So that value, we deployed that station in 2014. That station, we still deploy it every year. I'm sure we're going to keep deploying it for the next 10 years because that value is right where they want it, which is reducing risk. Shifting over to the buoys a little bit closer to my home. I don't know how I discovered this, and Dave Schwab is here, and someone told me this one day, that the only reason the buoys that there's buoys in the Great Lakes is because of the sinking of the Edmund Fitzgerald. And I think I told that for like 7 years to people. And I finally was like, I want to go find the evidence. And I found it again, and I emailed Carol Thompson from the Detroit News, and she thought that was interesting too. So she wrote a nice piece in the Detroit News, which is how the Edmund Fitzgerald sinking inspired advances in storm navigation. There's some real nice modeling and monitoring of the conditions that are happening. This was pulled from a publication that Dave Schwab worked on, which is what on earth was going on at the time the Edmund Fitzgerald was transiting Lake Superior. We certainly know there wasn't any buoys. There was a few casual observations. From what we can tell is the Edmund Fitzgerald was in the wrong place at the wrong time. And the waves and the weather experienced during this weren't unusual. They may be rare, but not unexpected. And it's what tools and informations should they have had before they were knowing they're on being in terrible weather, and were they ready for it? And the answer was no. And this was in 1975. By 1979 is when Congress authorized the first 8 buoys to deployed in the Great Lakes. I didn't find the budget bill or exactly how it was funded, but it was, hey, we do buoys, we need them in the Great Lakes right now, and let's make that happen. So they basically brought the ocean buoys to the Great Lakes. And I circled, this is a plot of the NOAA port page on Coast Watch, which shows all the buoy observations that they get. And I circled the original, call them the original 8. They're still deployed today. They're still funded through an act of Congress from the 1970s to have those buoys deployed via the National Data Buoy Center, put out by the U.S. Coast Guard. So one thing you'll see in the journey of sensors in the Great Lakes is we don't really lose that. So we haven't totally reorganized that every buoy now has to be deployed this way. We've just added to it. So I think these mission-based buoys are still there, producing great data. But it did take a crisis and an act of Congress for that to happen, and then to stay there. So big shift safety plus Congress equals 8 buoys forever. I don't know, absent another ship sinking, or there's been some. I didn't have time to go through the history of the Coastal Storms Program, another infusion of money and monitoring into the Great Lakes. But how do we get? My goal is how do we get more stations and keep them there, and work collaboratively on that. I did want to talk about a little bit of evolution in the platforms and the tech, and this is where my role becomes more interesting here, is looking at the big buoys that the National Data Center deploys. I think they make sense for the history of where that program comes from and the global footprint of what they need to deploy. In the private sector, we've thought a little bit more about how to help decrease that size, make them easier to deploy, think about the specific form and function for the user community. In our world, that user community, they live close to the lake. They want to know what the conditions are. There's some of our stations have been funded by the nuclear power plant. So different sensors go on that. So I think as we look at what the National Data Buoy Center started, how do we use new tech and adapt that and design things to be smaller? paying particular attention to the scale, how things are made, and how to maintain those. So this is a little bit of a time evolution of us working with a platform. This is the S2 Titus buoy built by a boat builder in Holland. Those buoys still exist. We still deploy them, but we've also built a smaller generation that's easier to deploy. We've thought about the weight and really the operation and maintenance. Like if we send people to deploy and maintain it, what is that incremental cost and how could that scale? And more recently, even trying to shrink that down further and make it easier to separate the smart and lighter components. Again, thinking about the transportability. So here's a look at our office next door where we just tow these on a small jet ski trailer. This is that S2 buoy. What gets exciting for me and where I'm really outside of my discipline training here is small scale manufacturing. How do we think about the form and function of these buoys and help manufacture parts that make it easier for us to use them? We've hacked and sawed and glued things that we can use to make these things more, but how do we have an original manufacturing process that gets things made from the beginning, and it looks better, it's easier to use, it's easier to make. So that's where Zach Gordon's in the room here, but he's a mechanical engineer that we hired, and it's been nice to just use that CAD and physical, like build the thing skill sets that he has, and to help apply that to this problem that we have of we want to deploy more buoys, we want to separate out the foam float parts from the electronics, and how do we help build those batches and maintain them. So we've built about 20 of these buoys now, about 15 of them are being used in the Great Lakes, and they just give us a custom payload and allow us to still put the equipment we want in, but to be easier to use and deploy. So here's another look at those. Again, very easy to collect all the smart parts, the batteries, and to separate out the foam parts. Once we start making the buoys smaller that still have a scientific use, we can still put ADCPs, we can still put instrumentation above the water. We can also think about how to scale a little bit better. So I wanted to focus on Southern Lake Michigan here. This is a look at all the buoys deployed in Southern Lake Michigan from the University of Wisconsin, wrapping all the way around to the little buoy in Muskegon. And what we've tried to support is other people that certainly don't have the ability to know all the electronics, but also driving our boat over and helping put the buoy in. So we worked with fishing clubs, communities in West Michigan, the nuclear power plants, Illinois Indiana Sea Grant, who does more fisheries work, and the Illinois State Geological Survey. So when we shrink the size of these buoys down, we can support more people with putting them out. They still get control over what sensors are on it, some trade-offs in quality and shape, but it's been a good example, I guess, of how we've built the instruments that we'll end up using for the next 10, 20 years, and thinking about how to just get more stations measuring scientific data as well as data feeding back to boaters. Moving over to Lake Erie, the density here, as you can see, the newest buoy we put out here was built in 2019 that we put out here. So in the last few years, with the manufacturing capability to get more buoys, we got a state project with the Cleveland Water Alliance that I'll talk about, but we deploy a buoy in every county near every major water intake, and deploy and maintain those out of our Ann Arbor office. So this scale has been nice to implement. It's been great to work with the Cleveland Water Alliance to really think about how to go from maybe 5 sensors is what the budget would have allowed previously in terms of the buoy cost, how to build it, to how to just do 10 or 15 at once. The operation and maintenance of this gets difficult, so but we're also to sorry. We also capitalize on just driving and deploying these all within a week. So we have buoy week in our office, and it's actually buoy month, really, where we're deploying buoys on Lake Michigan and on Lake Erie. And it's getting those stations ready, working with local communities to get those out. We've also connected the value again to the water treatment plants. So the city of Cleveland funds buoys near its water intake, city of Toledo, Aqua, Ohio now funds 2 buoys on the eastern side as well, and the Great Lakes Water Authority in Lake Huron. So again, we're trying to get that value back to who needs it and how to keep that buoy deployed. There's certainly other uses of the data that include scientific use as well as just general boating here. But again, a good example of building out a buoy network and having some sustainability plan for it. Talking about, so just trying to get to that scale, I mentioned the Cleveland Water Alliance. Our project that we're working on with them is called the Smart Lake Erie Watershed Initiative. And this is the concept that they brought to us, which is we need to have 200 sensors streaming real-time data on Lake Erie. It was a good tech challenge for us. I think we didn't quite get to 200 deployed all over the lake, but we thought more specifically about where should we be monitoring more, how to build that instrumentation and deploy it at a much larger scale. I did want to point out there was a 2021 postdoc, Jeff Pooh, that was co-funded here with Sigler and Limnotech, and Jeff's been a part of working on this project since then. So just a connection back to the lab here in Sigler for this project. This is the build out of the lake sensors that we've done in the last 2 years. So it's not 200. We focused on getting that 1 buoy per county and getting quite a few instruments on that buoy, which is the red dots here. We also worked to put in a new network of 10 weather stations and 10 water level stations that are the black dots on this map. So we really thought strategically about every 10 to 20 miles, we need to have a buoy measuring conditions. You can also see the existing light blue dots, which are the water treatment intake buoys that we had been putting out for years anyway. So how do we fill in this coastline, think about the stations, how to maintain those, and how to build that instrumentation at once. So we built all this instrumentation in 6 months and deployed it the next 6 months, and have a plan to keep these buoys in place for the next 10 years. A look at some of the batch building we did in our Ann Arbor office with the weather stations. We can see there was traditional weather, all-in-one weather stations that we would buy, weather sensors from Meter Group, how to package that with an open source data logger, how to add a solar panel and battery. So I think this is where our small scale batch manufacturing made this process go a lot faster than a custom build where we're ordering individual parts and then having to screw and drill components. So we sort of turned into our own manufacturer for this project, but then also had to maintain this instrumentation long term. It's certainly fun getting out into the coastal communities. They don't quite understand the barriers between how a NOAA weather station might get sited near them versus how can they have a coastal weather station themselves. It's interesting to see what either Davis or backyard weather stations end up at some of these yacht clubs. So I think our project brought some level of a professional level equipment and just started adding it in communities along the coastline. And it's good to connect back with who's going to use this data and why, and how do we share that data for better weather forecasting in the region. This is the city of Avon Lake. We actually, Avon Lake's not very big. We had the mayor, the utilities director, and the boat launch guy trying to figure out where this weather station is going to go. Just a look at that weather station deployed. So just climb up the tower, clamp it on, and walk away. I think that's one goal of ours, to make this instrumentation easier to deploy and also to maintain. Water level stations. This is a radar water level sensor. So this is the same type of instrumentation that would be used at a NOAA or USGS gauge. It's applied in a non-ideal location. There's lots of noise going to end up in this data, but we wanted to help boaters, especially in marinas and harbors that care about wild fluctuations in water level, with getting more information about water level. This instrumentation also has a non-contact temperature sensor on it, so we can get an approximation of the surface temperature with this instrument as well. Part of a goal of ours in the Cleveland Water Alliance is to help have more people understand what instruments are and to cross-train. So this project was half funded by a workforce development and tech innovation grant, which this is a community high school in Cleveland called Davis. They have a program called Argonaut, which has boats and trains high school students for careers in the nautical industry. We work with them to bring the buoys on their boat, talk about the electronics, the moorings, and to have them help put the instrumentation out. So it helps us lower our costs and also have a workforce training program to what we're doing. I think if you look at those 15 buoys, you know, we have an interest in how to help lower the, I guess, the knowledge gap between the people living there versus what tech is there. How can they do that for a career? And how do we help connect that data back to their programs as well? So just a good case study for workforce development and connecting the local buoys with the people that are living there. A good look at the size. Our boat is pretty small, so we certainly designed our instruments to be able to just be deployed by a small buoy or by a small boat with our smaller buoys. I did want to show some of the data. So that I've been mostly focused on how to help get this instrumentation smaller, make it easier to deploy. If I look at a subset of that data from this year, so these 3 stations on Western Lake Erie and 3 on Central Lake Erie, I wanted to just show you the wind sensor data and the wave height data. I do remember there was a time in our planning about having more sensors on the lake, whether we need more wave buoys or not. And again, Dave, I don't know why all these things are bringing up with you here, but Dave said we don't need more buoys, we have models. And I think, you know, that's stuck with me. And it's at some point, are the models right? Do we have enough local knowledge of that land surface exchange to know what the wind speed is, the surface temperatures offshore? There is a big data gap in water temperature, a big data gap in the breezes that set up in these local shoreline communities. So if I look at wind data between Toledo, Huron, Ohio, and Avon, it generally looks the same. There's some periods where it's not the same. It'd be curious to use this data set as a check along with the other NOAA observations. You know, is there a value in these observations long term? Were the models missing some key components? So you know, we don't know these unless we start measuring and generating the data and applying it. And if you're off on winds, then you're off on waves. So I think what Dave meant is the wave models are really good if you know the winds really well. And in this case, you know, wave height that's 1 foot versus half a foot might not seem that significant. You start to look at passing storms and events, you do see differences, whether you're in Toledo or over in Huron. So this is just from just a few weeks ago. I could point to other examples where, you know, large wave height differences, the models, how they're applied and how that data gets disseminated. People like seeing the actual observation more than thinking about a summary of waves 4 to 6 or 2 to 4. So it is nice to be able to have more stations and generate that data and think about our models able to capture this small scale phenomenon. Pretty significant differences here as well. I think we can look at the wind direction data. You can see is there directional components to what the models were missing. Going a little bit further over on the central basin side, again, showing wind speed here in knots at these 3 stations between Euclid and Ashtabula. We can certainly see differences between the wind speed and then differences in the predicted wave height as well. Here's just a brief snapshot of our sensor to cloud system, which is just how people can access data. We certainly know boaters want access to the data. This is just some simple web pages we've created. Data gets disseminated across NOAA and other agencies, but we've at least tried to have some visual tool of here's what the data is at our stations right now. Moving on to some of the challenges and advancements I've seen in this is connectivity. So some of the limitations on scaling in the Great Lakes is how to get that data back to the internet in real time. There's been advancements in cellular, satellite, and a new one called LoRaWAN. I think cellular, it's changing so fast. I could probably spend an hour talking about how cell has been changing so much. The takeaway here is you can pay $10 for a 10-year plan for a SIM card and get your data to the cloud for 10 years. So there's no monthly fee here. There's no, if you want a cellular device, put one SIM card in and you're done for a decade. Satellite, though it used to be maybe $40 to $50 a month per station. With new networks, it's about $5 a month. LoRaWAN here is coverage that we provide with a 900 megahertz system. It's a tenth of a penny per month. So cost isn't a barrier. The tech is available. How do we start taking advantage of this new tech at the scale that we want to, and not assume some, I'd say, dated plan of how cellular monthly plans are the limitation, and that's a problem. So I don't know if people are keeping track of the cell to sat world right now, but SpaceX has partnered with T-Mobile, and it's going to have a seamless connection of cellular to satellite. So you'll be able to use your cell phone anywhere on the planet and not care what carrier or how that data gets there. These same services are going to be available for sensors as well. There's another one with AT&T. I've been surprised at the pace of these technology being deployed. And the good news is we can keep deploying cell modems, and data is going to seamlessly use these satellite networks. And we won't have to do much. This is a look at just the SpaceX network, and this is satellite map.space. You can look at it yourself. Every white dot is a SpaceX satellite, blankets the globe. It's unbelievable. And those satellites are small. This is probably one of 5 or 6 that's being flown up into space right now. There's probably a dozen more that are planned. So getting data to the internet for a couple dollars a month or less, that's what it's going to cost. Cellular connectivity is poor offshore. I did want to put a plug in for this app called Cell Mapper. We've used this to help map offshore coverage. It's really tough to know what coverage you get offshore. There's some open source ways to feed your cell phone data back to these mapping companies to help plan for what instruments or what cell modems we need to buy and what coverages we do get. The other tech I wanted to mention is LoRaWAN. We've been working with the Cleveland Water Alliance to deploy this technology. These are very small radio modules that we can embed in our sensors, and then they will transmit their data to a gateway, and then that will get connected to the internet with a cell modem, and then make its way to a data system or data dashboard. That's that fraction of a penny cost that I showed. So if you wanted to get sensor data to a dashboard, it's one of the cheapest options available. Look at some of the sensor nodes here that are available that we've used, the gateways. One case study I wanted to highlight is deploying gateways in Toledo and Cleveland. We worked with the Glura Lab here to put a gateway on the roof of the federal building that covers a large part of the central basin. It's about 400 feet high. And one thing we did this spring is we took a GPS mapper, put it on the Lake Guardian on the top, and they've been driving that device around all spring. So this is a map of their ship track as logged by our tiny little $5 LoRaWAN radio device inside that gets coverage across Lake Erie. So this LoRaWAN is available. There's a partner network I didn't talk about, which allows some roaming called Helium. So there's LoRaWAN coverage in many places right now. And it's been really nice to see that we just stick this small thing on the Guardian and boom, we get a coverage map. So it's new tech. How do we think about why should we be measuring things at this large scale? And how do we help just use the tech that's available right now? A little case study looking at us building a custom data logger. The H2 Ohio Wetland Monitoring Program came to us with the challenge that we need to monitor 170 plus projects in the state, and we need to deploy hundreds of sensors. We ended up working with them to build what we call the Otter, which is, it's just a custom open source data logger that has a built-in solar panel on the backside. It's got the connectors, an SD card, cellular and LoRaWAN connectivity. This ends up looking like a commercial product. You know, we could sell this. I think we sort of built it as our expertise to the project, and the contribution was getting the requirements and then building these and delivering them so they can use them. It's been good to know that that is that business model. We don't have to sell this if we don't want to. There's challenges of using open source and selling that. But I think that science group came to us with our old method is us drilling and screwing all these things together to take advantage of that open source board on the inside. How can you help us build this, and we can just start using that open source platform. A little look at that batch manufacturing. Again, just the cost of things cuts in half or even less when you think about the scale of just doing it at once, and then actually starting to use that equipment. So I've got to look at us building some of this instrumentation in our Ann Arbor office, and then a photo of it being deployed here. So there's instruments in the water. You can just strap it to a pole. I'm want to leave time for questions. Mention real quick our last project using sensors at scale. This is a new project with the Michigan Department of Agriculture, the Alliance for the Great Lakes, and Michigan State University. A portion of it was also funded by the Herb Family Foundation. But our goal was to apply a lot of the sensors that are used in the watershed at a scale that we haven't seen before. This is actually the lab is here. This is South Ann Arbor, Saline, and this is the Saline River watershed. The state has been targeting these sub-watersheds, 5 watersheds, priority sub-watersheds. They're all agricultural dominated, and we wanted to monitor water flow, turbidity, automated water samplers, and online nutrient analyzers at all these locations. So this is a 5-year project. We're deploying about, this doesn't get into the parameters, about 200 or 300 individual instruments that'll be located on bridges, streams, and culverts. And we'll understand when it rains, how much turbidity rises at all these stations, what's the flow, what's the nutrient concentration in these subwatersheds. So this is our first applying tech at that watershed scale and really thinking about the cost of the instrumentation. One case study, the water quality sensors, once we got into a volume order of these Yosemite sensors, the price was cut in half. So, you know, until you talk to manufacturers, it's tough to know some of the scaling capabilities. So we were able to double the number of turbidity sensors by just doing the volume that we wanted to on the project. Here's a look at us building some of these right now. This is just here this past week of getting all this instrumentation, building a custom housing, and working to get that instrumentation eventually out into the field. This is a radar velocity sensor I'm showing here. So we're trying to use instruments that are cutting edge, save time and labor. Okay, that was my run through. So I talked through how to think about sensors, where we're adding value and where those sensors are connected to that value, talking about sustainability. And that's been the real challenge. I think the private sector has to think about that on a daily, yearly basis. It doesn't mean we don't like doing it. We don't, we sort of enjoy that sustainability challenge. We also enjoy that operation and maintenance challenge of how to think about the people power to maintain these. I also want to have people think large and ask why not more often. So why aren't there more sensors deployed? And the cost of scale is cheaper than you think. Lots of case studies of that. And just building it and deploying these things, it is quite a bit cheaper. Last one is have fun. This is a picture of the University of Wyoming that we worked with to get some buoys out last year. These are science researchers. They've worked with the YSI, but a floating platform with a mooring and the science instruments. They were just so excited. Will here, he just like, I just want to jump in the water and go swim to the buoy. So it was nice to see that enthusiasm transferred and them just like, yeah, this is what we wanted. This is what it's supposed to do. So that's been a fun part of the working with this technology and transferring it to other locations. I did want to acknowledge all the people that make this happen. Some are in the room here today. And I'll take questions with the time I have left, and I'll be around as well. So thank you.
We have time for a couple questions. We'll start in the room.
So I'm curious about the proportion of the cost goes into like purchasing materials, sensors, or is it more going to the research and assembly in limnotech?
Yeah, I think if you look at even the buoys or some of the recent things, it's about a half. So about half might be the physical, like the thing, and then the other half is the labor. There's some part of the process is actually designing it and thinking through that process. And once you get all through that, it's easy to just do it. And I think that's where the engineering side helps with that. There's going to be some upfront engineering cost, and then there's this. Once you build and do that, it's cheaper to do the next batch. So, but about half and half is the split for labor versus parts.
This is exciting, Ed, to see this stuff after I've been working on it for so many years, and the latest things are just mind-blowing. But you mentioned the usefulness of models versus data, and in my experience, there's a symbiosis between models and data. Each one enhances the value of the other. You can't have a good model without good data, and the data is enhanced by having a reliable model to fill in the gaps between the data and to forecast. You know, a good example is the way the Weather Service works. If you look at how the Weather Service is invested in data gathering and modeling, I think is a good example for what you might want to strive for over water as well. Then the question I have is, how does GLOS figure in this? I was around when GLOS started, and many of the things that you're addressing are the reasons that GLOS was started. And I hope there's a funding stream coming through that to develop some of the concepts you were talking about.
Yeah, I think GLOS has really helped to organize some of the federal implementations of that, and I think as a NOAA, affiliate, they're sort of responsible for that that interface between NOAA and what else is going on. Our sort of jump over to the private sector there's lots of things that are NOAA or even GLOS doesn't quite get over to the, do we charge per access to buoy data? So how to connect things at the scale that the private sector is just going to keep doing and working. So I think there's just a difference of the NOAA versions of how those networks grow versus just how communities or manufacturers or things just end up out in the lake. So I think we're attempting to bridge both of these as having a research background. I know how to grow nodes of scientific work, but I also just want to see more sensors out too. GLaDOS is an example of like, where did that come from? I mean, they certainly talked about it and planned for it. And how did we intersect? And how did that community end up so tech dense? And what can we learn from applications from that? So that sort of connecting to value thing, I think given NOAA's tax base, how do they grow goes to Congress. How we grow grows to, does someone want another buoy and do they want to keep that there? So time and space and politics get involved with how one grows or the other. I'm certainly interested in more, how do we maintain all the instrumentation, add more, and think about scaling. Your point about model and data, I always saw that as a one-to-one. There's this other AI machine learning animal that's just crept right in and is probably the largest thing in the room right now. And so I think the word model is, it's not that it's dated. Like I'll say I use that, and data is more empowering for people in building from that understanding forward. So I think I've sort of jumped over to this data side, and I want to jump back over, but I don't know where to land on the modeling side anymore. Like it's really hard to know where those tools are going to be applied, how to help, and that's where the private sector is going super fast. Like it's really hard to know how to apply those AI, and I mean they might drive us out of business because AI is you just ask AI what the wave height is and it knows. I don't know how it knows, but it's going to know, and it's from data from years ago. So anyway, I'll stop there.
Yeah, we're at time, so we'll stop there. But like Ed said, he's going to be around. He'll be having lunch in the lunchroom, so please feel free to join us. Be happy to chat, I'm sure. And thank you for coming, and let's thank Ed one more time.